Okay, in this video we will be focusing on a new type of reaction that you have not been exposed to called the redox reaction, also called oxidation-reduction reactions. We are going to do just a very introduction part in Chapter 4. We will be doing a lot more later in the course when we do an entire chapter on oxidation-reduction reactions. But basically an oxidation-reduction reaction is one in which electrons are being transferred from one atom to another. An example of that is this reaction shown right here, which is the reaction of sodium metal. You see a chunk of sodium metal with all the sodium atoms organized like metals do, reacting with chlorine gas, which is Cl2, two chlorine atoms bonded together, these gaseous molecules moving fast, and these two substances collide with each other and react to form sodium chloride, which is your table salt. In the past, we maybe called this reaction a synthesis reaction, but upon closer look, we can see that the oxidation state of each of these substances changed. If we assign oxidation numbers to the sodium and the chlorine gas, you might remember from a while ago, that the sodium oxidation state is 0 here because none of the sodium atoms are pulling electrons harder than any of the others. Also for the chlorine, it's the same thing. Each chlorine atom is given an oxidation state of 0 because they both pull on the electrons equally. However, when you have the bonded sodium chloride, the chlorine pulls much harder on the electrons and is given a -1 oxidation state, while the sodium is not pulling as hard or has less electronegativity, and so is given a +1 oxidation state. When you have a change in oxidation state, we say that there has been a transfer of electrons, and this reaction would then fit into our redox reactions. You'll notice that I had to assign oxidation numbers to realize that this was a redox reaction, so we might want to go back and review the rules for assigning oxidation states. The oxidation state of an atom of a singular element is 0. Like I just said, the example of that would be like hydrogen gas. Neither hydrogen pulls hard. A chunk of silver, all the silver atoms would pull equally on the electrons. Any diatomic molecule or metal chunk, they all are going to have oxidation states of 0. The second rule, or the second example, would be a monatomic ion. Anytime you have an ion, the oxidation state will be the same as the ion's charge. For instance, sodium 1+ would have an oxidation state of +1. We kind of talked about that. When we write charges, they will be written with the number first, then the symbol of the charge. When we write oxidation state, the symbol will be written first, then the number. The next rule is, oxygen will always be a -2 in covalent compounds. There are a few exceptions to that, and that's in peroxides. For instance, if I write hydrogen peroxide, H2O2, the oxygen actually has a -1 oxidation state, leaving the hydrogen with a +1. This doesn't happen real often, but it does happen, and so you will want to know that there is an exception to the oxygen being a -2 oxidation state. Rule number 4, hydrogen's always a +1. 5, fluorine's always a -1. Number 6, if I have a compound, the oxidation state must add up to what the charge of the compound is. Therefore, if the compound is neutral, which it should be, the oxidation states should add up to that. So chlorine's a -1, which means sodium must be a +1. If I have carbon dioxide, I know that oxygen must be a -2. If I have 2 oxygens at -2, that leaves carbon to be a +4. The sum of the oxidation states in your compound must add up to neutral, or 0. And then the last rule is the sum of the oxidation states for a polyatomic ion must be the charge of the ion. So for example there, you have NO3-. Each oxygen is a -2. So I have 3 oxygens at -2, that would be -6. My nitrogen then would have to be +5 to make sure that my oxidation states added up to the charge of the ion. Another example could be nitrite, NO2 minus, and so each oxygen at -2 means a total of -4 there, so my nitrogen must be a +3, again, to add up to the charge. You have to be able to assign these oxidation numbers to even begin to solve any type of redox reaction problems. So in the following here, I would like to have you assign the oxidation numbers of each of those atoms, and then I will, you pause your video, try them, and then I will give you the answers. So push pause now, try the assigning of the oxidation numbers, and then start again to get your answers. The answers are potassium is a +1, chromium should be a +6, and oxygen you should have gotten -2. In the next one, I'm going to write it over here. The carbon is a +4, and the oxygen's a -2. For the next one, your manganese should be a +4, and your oxygen a -2. For your phosphorus, it should be a +5, and your chlorine a -1. And then the last one is SF4. Your fluorine's a -1. Your sulfur should be a +4. Hopefully you got those correct using the oxidation rules we just reviewed. The next thing that we need to talk about are just some characteristics of the, now we're going to go through all the answers again. Some characteristics of the redox reaction. I already said there will be a transfer of electrons. This transfer may occur and it might end up forming ions, and that was kind of the idea with our sodium reacting with chlorine, formed sodium and chloride ions, which then were attracted to each other. The substance that loses electrons is the substance that we called is called being oxidized, or it's in oxidation. It is also the reducing agent because it causes the other substance to gain electrons and decrease oxidation state, called the oxidizing agent. A little mnemonic device, or a way to remember this, is Leo goes grr. And what this means is if a substance has lost or lose electrons, it is oxidized. If the substance gains electrons, we call that substance reduced. So we are going to practice this in the next slide, but a loss of electrons, that substance is oxidized. If a substance gains electrons, we say that substance is reduced. So here is a practice problem. Which of the following are oxidation to reduction reactions? And then identify the oxidizing agent and the reducing agent. So in order to identify the oxidation reduction reactions, we need to assign oxidation numbers. So for the first one here, move this out of the way, I have zinc, and because it's not bonded to anything else, it has an oxidation state of 0. The chlorine's a -1, hydrogen a +1. Here, chlorine -1, but because I have 2 of them, the zinc must be a +2. And then hydrogen is not bonded with anything else, so it, oopsie, is going to be a 0. So as you can see, the zinc went from 0 to +2. The hydrogen went from +1 to 0, and the chloride remained the same. But because I have 2 substances changing oxidation state, that means that this must be an oxidation reduction reaction. Now to identify the oxidizing agent and the reducing agent, the substance that was oxidized is the reducing agent. The substance that was reduced is the oxidizing agent. So I'm just going to draw a line here from my zinc to my zinc. My zinc went from an oxidation state of 0 to an oxidation state of +2. In order to have that happen, it had to lose electrons, so it must be oxidized. That means zinc is the reducing agent. So zinc, the atom, was oxidized. Zinc also is the reducing agent. Looking at the hydrogen now, hydrogen went from a +1 to a 0. In order to go from a +1 oxidation state to a 0 oxidation state, there had to be a gain of electrons, so hydrogen was reduced. The hydrochloric acid then is the oxidizing agent. So, to repeat, an individual atom can be oxidized or reduced. The entire substance or molecule is the oxidizing agent or the reducing agent. The agents must be in the reactants side. The substance that was oxidized has to be an atom or an ion on each side of the reaction. So I want you to try letter C here. Pause the video. Try letter C and identify what is the oxidizing agent and the reducing agent, or if it is a oxidation reduction reaction at all. And as you can see, letter C here is an oxidation reduction reaction. What you should have gotten was that the copper here went from a +1 oxidation state to a +2 oxidation state. So this is a +1, this is a +2. That means that the copper lost electrons, went to a more positive state. That means it was oxidized, and so this is the reducing agent. The funny thing is here, some of the copper also went to a 0 oxidation state. So again, the copper, in this case, gained electrons, and it was reduced, leaving the copper chloride, again, to be the oxidizing agent as well. So it is both the oxidizing agent and the reducing agent, and the copper atom was both oxidized and reduced. Kind of unusual. We can use the idea of oxidation reduction to balance reactions. Here are the steps we are going to follow. I'm not going to read them all to you because we're going to use them in an example. But we are sometimes required to use these steps to balance a reaction. We can't just do what we've done in the past by adding up atoms and looking at coefficients.